One of the things they've asked me to do today is give a short course on energy release here, and as we do that, I want to explain to everybody kind of how we came about. One of the things that, you know, the properties of oil, when you pick up a good brand of oil, one of the things that they wanted to do when they made oil was to make it slick so that moving parts could move friction-wise against one another a lot easier. The other property that oil has, and that's called lubricity. That's how smooth and how slick it makes things. The other property that oils in the lubricating class have is called viscosity, and that's how thick they are like syrup or how thin they are like water. And one of the reasons that they build viscosity into oils is that you not only have friction surfaces that rub against one another, but you have shock surfaces where, like the piston moving down on the connecting rod and pushing it against the crankshaft. So as oil is pumped into those orifices between the moving parts, it makes a cushioning effect in there. And that's one of the reasons that we develop energy release is when oil goes away and you have no more lubricity, the slick stuff, or you have no more viscosity, which cushions it against the shock loads, then that's when our product energy release comes into play. And what it does is it makes metal itself so smooth that even though you get heavy shock loads on it, it can't scuff. And so we're going to demonstrate that with a little machine that we call the pin and block test. Now, over the years, if you've been the kind of person that's been interested in automotive mechanics and engines, you've seen a lot of tests run with a little machine that's called a friction brake machine. And what it does is scuff a little roller bearing on a roller bearing surface on another ring in there. And we found out that that distributes the load quite a ways, and so we developed this little thing called the pin and block test so that we can get a lot more pressure in a lot smaller place. This is a pin, and you can see it's just like a dowel pin. It's like a drill blank without any blades on it. And this is what we call the block. It has a little 1/4-inch hole drilled in it, and the two pieces are made of such dimensions that you've got about the clearance that you have in a car on the crankshaft and the rods, or like the wrist pin. You got about 1/1000 clearance in there. So it just spins freely like that. And what we did is we took a drill press type mechanism and we chucked it up. And it has a torque wrench up here. You can see this gauge on it. And that allows us to measure the amount. And we put this block in this little vise down at the bottom so it all gets lined up properly. And then we can put lubricants like this standard brand of oil. We'll put just a couple of drops of that standard brand of lubricating oil in this little block right there on it. Just fill it up. As you can see, I got it all over everything, but that helps make it slicker. We'll start up this drill, and then we'll bring down that arm, and you can kind of watch if you wanted to see somewhere between 20 and 40 pounds or even less. It will lock up because that's what that's designed to do. I'm going to go real slow. You feel a vacuuming effect as you push the oil out of the way. Now if you watch that gauge, it's now stalled, and it's about 40 pounds on there. It locked that bit in there. In fact, it locked it so good that it tore it out of the chuck on the drill press there. This pin is totally locked in there. And if you could get up close with a zoom up, you could see little torn places around the shaft where the chuck of the drill press locked in there and just froze the pin. So you can see that's what happened. It takes somewhere between 20 and 40 pounds to do away with that. Now I'm going to do the same type of test. We have another little pin and a block. Same thing. It spins easy in there. I'm going to chuck this little one back up, and we're going to do the same kind of a test, only we're going to do it this time with energy release. It'll give you a kind of a comparison of what can happen there. Do the same thing, only instead of using the green, we're going to use energy release, or as a lot of people refer to it, ER. Same little test. Start the drill. I want you to pay particular attention to this time. Now I'm getting that hydraulic effect of pushing the ER out of the way. We're now at the bottom of the hole. as you can see, you can take it through to the bottom, but you can't stop it. Now, one of the things that we find out about energy release after being in the business for years is that it has a residual effect. Because what we're doing is filling in the pits in the metal, not with another substance that makes oil slicker, but with a substance that's right there. And so we make the surface so smooth that it can't gall. And now to show you that there's a residual effect, what I want to do is take one of these little Q-tips and just wipe out all of the oil that's in that hole. Could I have an unbiased observer come up here, please? Somebody just step up here. Take a look in that. Tell me if there's anything left of the lubricant in that hole.
There's nothing in there.
Okay, and we're going to wipe it all off. We're going to spot. So this is perfectly dry now. And to prove that let that run down. To prove that we have a residual effect without any of the lubricant there now, we've taken it away. We want to show that we've treated the metal and made it so smooth that it can't gall even when the lubricant, the energy release is gone. As you can see, it's now treated the metal. But the basic thing that I want to show you is the shock load capabilities. If you're depending on the viscosity of the oil to keep two metal surfaces from galling because of shock load, and that viscosity thing, the thickness of it goes away, you immediately bind up the metal. That's what we did with the oil at first. But I want to show you that once we do what we do, which is a total departure from using lubricant, is changing the surface of the metal, then you can't gall it even though put immense shock load. This is the test of proof. I'm going to shock that piece of steel that would absolutely lock with any kind of lubrication. The fact is, you cannot break through it to gall the metal because the philosophy that we have, the type of discipline we have, is totally different than oil. It keeps the metal so hard and smooth that you can't break through it and shock it. That's the difference between energy release and lubricating oil.